Hi everyone, today I'm going to talk to you about abstracting fairness, oracles, metrics, and interpretability. This is joint work with Cynthia, Dwork, Christina, Ilvento, and Rothblum. So the motivation for this work is the notion of counterfactual fairness, which is an inspiring notion put forth by Kushner et al. In 2017. This notion states that an individual and their counterfactuals should be treated similarly. Precisely, consider a setting where you have a bunch of data on individuals where your observed variables are x, a, and y. Maybe x is a vector of features, a is your sensitive attribute. For simplicity, let's say takes two possible values, and y is the response or outcome you're interested in. Then a predictor y hat is said to be counterfactually fair if for all possible choices of values of x and a, the probability that the predictor takes a particular value, small y, conditional on the fact that x and a take these specific values, is the same as the probability that another predictor, which we will describe soon what it is, that this other predictor takes the same value, conditional on the same event. And this should hold for all possible choices of small y. So what is this y hat sub a prime to a? This is the version of your predictor, but in a counterfactual world where the value of the sensitive attribute is switched to a prime, which is the other possible value it could take. And how should one construct these counterfactual worlds? This counterfactual world really tries to capture what happens if you set a to a prime, everything else being equal, but this everything else being equal is captured using a causal model. So what is a causal model? A causal model is you specified, one way of specifying it is through causal graphs on the observed variables x, a, and y, and possibly some other unobserved variables u, which are also relevant for your task. And such that the arrows, these directed arrows on this causal graph actually indicate how a variable causally influences another. But to specify the full model, you also need to specify the functional relationships between all of these variables. And there are sophisticated rules then saying how you should really construct a counterfactual world where the sensitive attribute value changed, and then you kept track of all these causal relationships, and then you can create a predictor, a version of your predictor in this counterfactual world. For more details, see causal inference textbooks. But the point is to compute these counterfactuals, you need to have complete information about the causal model. So this is a very interesting proposal. It's elegant and seeks to capture individual fairness through the lens of counterfactuals. But what is the issue? As we already pointed out, these counterfactuals are calculated under full specification of the causal model. And this model needs to be accurate for this to be useful for fairness in some context. And what are the specific issues with this? One, the same predictor may or may not be counterfactually fair based on the causal model. Now, different causal models may also give rise to the same data distribution. And this is a classic problem of doing causal inference from observational data. So just looking at the data, you never really know which causal model would be the right model to look at. And finally, what all this means is that the counterfactual worlds you create can differ widely based on the causal model, and then your conclusions about which classifier is fair or not can also change a lot, even for many other things remaining the same. And in a later work, Ilvento et al. Summarized nicely the sensitivity of this procedure to unobserved variables of certain kinds. Now, it is not surprising that if a definition of fairness is heavily reliant on a particular kind of modeling assumption, and then there are errors in modeling that can lead to dire consequences. But let's go back to this famous maxim due to George Box, which says that all models are wrong, but some are useful. So how would you really know when your model is useful? Maybe it is wrong, but maybe it's sufficiently close to the true causal model that it still ends up being useful and still ends up producing classifiers which are reasonable from the perspective of fairness, if you, for instance, use counterfactual fairness. So to operationalize such definitions like counterfactual fairness, which rely on a model, we do need side information on the validity of the causal model or how useful it is for the particular task at hand. So let's assume that we have an oracle who gives us this information or who understands the true causal model. The question we pose in this talk is, what it is can we learn from such an oracle? And as we shall find out in this talk, we can learn a surprising amount from such oracles. But before I go on further, I'd like to make a general comment, and that is, It is well known that context is crucial for the purposes of fairness. This is not something specific about counterfactual fairness, that you need to understand the causal model well, but a lot of fairness definitions comprise two interacting components. One is the technical condition, and then there is another context. There is an accompanying context or auxiliary information you need to evaluate if your classifier satisfies the technical condition. We already saw what this means for the counterfactual fairness notion. For metric fairness, this is in the form of a Lipschitz condition and then a metric, and the notion says that similar people should be treated similarly, where this similarity is governed by the metric, which was pre-specified to you. For multi-calibration, this is in the form of the calibration condition and then a collection of sets with respect to each member of which you would like to have your predictor to be calibrated. And this list can go on. Some group fairness notions can be cast in this framework if you think of which protected groups, which should be the protected groups, if you think of this to be the desired context that should be specified. So the main point is context is crucial, and different contexts can lead to different conclusions in all of these cases. And there's a recent work by Baer et al. In 2019, which includes wonderful discussions on the importance and relevance of context. So what I really to say about counterfactual fairness throughout this talk is sort of a general theme, and these other definitions, which also include or needs one to specify a context, also fall in that setting or that general framework. Okay, so for this work, what we're going to do is we're going to fix the task and the fairness definition W, and let's call the universe to be X. Now, such a fairness definition can actually be completely identified by a list of context classifier pairs. So, you know, if you just write out, if you could write out possibly the set of all context and classifier pairs which satisfy this definition, then you can equivalently identify W that way. So what we asked ourselves is, suppose we have an oracle or access to an oracle who can which has a notion of, or which understands, or which can tell us which context classifier pairs are truly fair. So, and what we can do is, with such an oracle, we can feed in context classifier pairs that satisfies this definition, and the oracle will output accept, reject, based on some true notion of fairness. As an outcome, this oracle ends up being associated with a set tau of classifiers, which is all the possible classifiers for which are acceptable to the oracle under some context. Then what we achieve in this work is explicit extraction algorithms that recovers this list tau of classifiers or approximations thereof. And this is applicable for any technical plus context type fairness definition. Now, in particular, what ends up happening is our algorithms end up producing a coarse metric, because any classifier this oracle accepts automatically induces a partition of the universe into two groups if we consider binary classification. So let's just go with binary for the rest of this talk. And then that is naturally a coarse metric, okay? Now, you can utilize this threshold combination procedure of Ilvento, which is also going to come out in 420, and use this to enrich these coarse metrics. So the outcome of our algorithm, an upshot of our algorithm, is learning of such coarse metrics. Okay, so what does all of this mean? As we already argued, fairness definitions need to incorporate context into them. And for that, one needs to reason about when or whether a given context is appropriate for the task at hand. Now, whenever you think or you have such ability to reason about this appropriateness, it implies, our result suggests that this implies that one has some loose notion of a metric or understanding of a coarse metric. In parallel, our work also has implications for interpretability. Now, interpretability has often been espoused as an alternative to ensuring fairness. It has been looked at for other reasons as well, but we're only focusing on fairness here. And interpretability fosters fairness by allowing an auditor to reject classifiers that are deemed unfair. So our extraction procedures or extraction algorithms in this work imply that existence of such an auditor means existence of coarse metrics, and these metrics can be extracted by an automated procedure by interacting with such auditors. So in a sense, what all of this means is that if you have access to fairness oracles who understand the context, or human arbiters who can rule on unfairness when they see it, in a sense, they're functioning under some notion of a metric. It can be coarse, but so there is no eluding trying to understand some version of a metric which is relevant for the task. Okay, so moving on, the specific setting will be, there will be a fairness definition W, which as we saw can be captured by context classifier pairs. Recall our oracles are associated with a set tau of classifiers, the set of classifiers which it accepts under, each of which it accepts under some context. As a specific example, if W is counterfactual fairness, then maybe the oracle knows the true causal model and is willing to only accept classifiers that are deemed fair, that deemed counterfactually fair with respect to this true causal model. So that's one way you could think of it if you have counterfactual fairness in mind. And some notations for any classifier C, let's just say C sub I is the classification for the ith individual, and also further assume that the number of total possible contexts is bounded by a function of the cardinality of the universe. This is not a strong assumption. If we cannot even enumerate all possible contexts, then it's unclear how we are going to implement this notion W for the task at hand. Okay, so for this strong oracle, naturally, then there exists an extraction procedure for which the running time is a function of the cardinality of the universe that can interact with the oracle and output the set tau that is associated with it. And this is, of course, not difficult to prove. It's very trivial. You could just do this via exhaustive search. So this preliminary result, it really just has conceptual contributions. And once again, what does this say? If you think of the oracle as a human expert with knowledge of true functional relationships, but is unable to enunciate them, then there exists a systematic procedure that interacts with the expert and learns the truth. One consequence of all of this is that if you wanted to, for instance, implement counterfactual fairness, and if learning the true causal model is hard, this suggests, having such a systematic procedure suggests that maybe if we could develop efficient query models, hopefully that will lead to efficient recovery of metric, and then one can use other techniques to achieve fair classification. Okay, so that was sort of a preliminary result. Now, what is interesting to look at is not the original oracles because they were too strong, but a relaxation of them. So let's fix a strong oracle with an associated classifier set tau, and delta is some positive constant. Then we define a delta weak oracle for a function D to be an oracle that accepts all the context classifier pairs that are accepted by the corresponding strong oracle. And this rejects context classifier pairs if the classifier is further by distance delta from every element of tau. Okay. But then this oracle actually behaves arbitrarily on the remaining elements. And this is the weakening because there could be lots of context classifier pairs where we don't really know what the weak oracle is going to output. Okay, now based on different choices of this function D, we can have different instantiations for the weak oracle. We could look at the Hamming distance, for instance, and for this, under mild conditions on tau, exhaustive search recovers approximations to tau. So that's not difficult to prove. Or we could look at other definitions that's based on pairs of individuals. So we can look at the transportation cost, for instance, which is the fraction of pairs of individuals for whom the first argument, T here, assigns the same classification, but the second argument, C, does not. So this is an asymmetric cost function. You could also look at a symmetrized version of this, but actually among all of these, it's the asymmetric transportation cost that's going to be the hardest to deal with. So we'll just present the results for that here. Okay, so the goal is to recover members of tau from a weak oracle based on the transportation cost. Let's denote tau in this form. It has L elements. And then for any classifier U, we define U0 to be the number of the indices which assign the classification 0 under U, and U1 is defined analogously. Then what our algorithms do is they produce a list of classifiers of cardinality 2L, so twice the cardinality of the set tau, such that for each index j, so if we fix an index j, there will exist a unique member in tau such that the classifiers pj and qj correspond to tj in this particular sense. So if you look at the elements which are labeled, which are classified as 0 under pj, that is a subset of elements classified as 0 under tj, and the error on the other part is small. So if we look at elements classified as 1 under pj and intersect that with elements classified 0 under tj, that is small. And qj has similar properties, but with respect to tj1 instead of tj0. So together, this pj and qj recovers a large part of the elements classified as 0 under tj and as 1 under tj, both these groups. Okay, so a quick dive into the algorithm. It has 2 stages. The first step is a clustering procedure, which produces a list of clusters of classifiers with very nice properties. So each of these clusters corresponds to a unique member of tau. And all of these, so if we fix the cluster Cj, then all the classifiers within it agree with either Tj, the unique member of tau that cluster corresponds to. So it either agrees with Tj or its flipped version, 1 minus Tj on many coordinates. Further, Cj contains either Tj or Tj prime, or Tj prime is 1 minus Tj. So depending on whichever one things agree with in the second, in the point above. But the thing is, these are clusters. They contain, either Tj or its flip, and some other elements, but we do not know which one is Tj, for instance, or which ones are close to it. So the second step achieves this. To complete the algorithm, let's define an operation called merge once, which produces, given any 2 classifiers u and v, merge once produces a new classifier w, such that the elements classified as 1 under w is a union of the elements classified as 1 under either u or v, and everything else in w is assigned to 0. Then from these original clusters, you produce subsets such that, okay, so how do we define these subsets? Fix an element from Cj, and then look at every other element from Cj, and see if merge ones of this original element u with this other element v is also a member of Cj. So this is asking for closure under merge ones for all of the other elements of Cj, and just produce a subset of classifiers of this form. And finally, we output a classifier which does merge once on the smaller subset. So looking at this picture, Cj was the original larger cluster that was produced, and Cj is typically a much smaller cluster, and then Pj is obtained by merge ones of everything in this smaller cluster. And because of the properties of merge ones, Pj itself actually belongs to this cluster. Furthermore, one can show that in the stage 1, step 3, if Tj is in Cj, then Tj will also belong to this smaller cluster. And in fact, Pj is the classifier we wish to have. It has the nice properties. We were looking for the zeros classified, the elements classified as zeros under Pj is contained, or is a subset of elements classified as 0 under Tj, and the error on the other side is small. We can precisely quantify what this error is. Here, tau is the cardinality of, is the cardinality of Tj0 divided by cardinality of the universe. Okay, so fraction of pairs in the same group in Tj that are split by Pj remains below delta. You can calculate and show that. And because the weak oracle gives us fuzzy information where there is a delta margin of error, this is in some sense the best you can hope to do. Okay, so wrapping up, as we argued, context is absolutely crucial when we're talking about fairness. In this work, precisely because we present a concrete framework that talks about regarding how to talk about fair and wise human judges. But the main contribution is really existence proof. So we show that we're able to extract metrics from such oracles or fair and wise human judges. And that means that to operationalize counterfactual fairness type definitions or all other definitions which fall in our framework, one needs, or this oracle needs, an understanding of some form of metric, even if it's a coarse one. And in turn, this ends up connecting seemingly unrelated notions of fairness. And we hope that this work is going to inspire more work in investing in metric learning or investing in efficient query models when we have access to such oracles in settings where it's possible to build such efficient models. And finally, we also saw that if we interpret the oracles as human arbiters or auditors who can rule on unfairness, then our work has implications for interpretability. Thank you very much for your attention, and this is my contact if you would like to pose any questions. Thank you.